Thank you. And by way of introduction, I'm a professor of electrical engineering and physics at the University of Virginia. I also have a side job as their chief academic officer and provost. But I was a co-author of a previous report, the High Energy Density Physics Report, The X Games of Contemporary Science. And you know what I loved about this report, Roger, is it starts with a humanist touch. It begins with a quote from H.G. Wells, as you recall, and it captures the human fascination with light, and particularly high-powered beams. And H.G. Wells says something like, he describes focused beams of invisible light in the presence of which lead runs like water. And of course, the reality is much more exciting than that. When matter is placed in the presence of the might of these high-powered lasers, much more exciting physics takes place. And I'll mention a couple of examples. The first is what happens to the vacuum itself. So there is something called the Schwinger limit, and above that limit, even the vacuum is torn apart, and it's somewhat akin to what happens in some cosmological models of an expanding universe. At some point, the forces that are driving the universe outward become so large they tear apart the vacuum, and the vacuum begins to hemorrhage particles. We can't actually reach the Schwinger limit in the lab with present generation laser technology, but you can begin to approach it. You can do something called boiling the vacuum, which is akin to that. What you do is send a couple of petawatt lasers at each other and begin to boil the vacuum. And you can detect that by sending a third laser, which would normally at low intensities go right on through. But if there's something going on and particles are being, there's some probability of particles being created and annihilated, through quantum mechanics, you can scatter off that probability density and actually bend the light and detect that there's something going on. So you can begin to probe what is the nature of vacuum itself, which I think is pretty exciting. But then what happens when you put matter in the presence of these high power lasers? If any of you has a sixth grader, you know that they'll tell you that there are 4 states of matter, but it's not that simple, right? So you imagine, solid, liquid, gas, plasma, and then getting to the point where you have something hot enough to be a plasma, but now you take one of these high power lasers and use the radiation pressure to squeeze that matter down to solid densities. Well, it begins to behave much differently. In fact, you can form charged crystalline structures. So what state of matter would that be on your 6th grade homework test? It's really something quite different. In fact, we don't know how that behaves. One of the big unanswered questions is, what is the equation of state of such a state of matter? And it has profound implications for models of the evolution of large planets and some stars. So these are important questions. It also has ramifications for the states of matter that are relevant to inertial confinement fusion and fusion energy. So these are big questions. And the other applications of these lasers are in the area where I've done research is laser plasma Wakefield accelerators. And when you think about the fields in these lasers, that you can use a unit of 1 TeV per meter, right? 1 TeV, tera electron volt, is the energy threshold for the frontier for high energy physics. And so you 1 TeV per meter. And in contrast, conventional accelerators are long microwave ovens, and they push particles at a rate of 1 TeV per 100 kilometers. And that suggests the scale of miniaturization that might be possible. And then you could start thinking about the many applications of such accelerators to things ranging from discovering new particles like the Higgs boson to medical treatment of cancer and medical imaging. So the science is promising. When I took a quick survey, I looked at the Nobel Prizes in recent decades. I counted about 24 recent Nobel Prizes that involved in some way advanced laser technology. So there's a lot of promise here.
Thank you, Tom.
Did you want to ask me about a second question, or?
Why don't you go ahead?
Yeah, well, so I'm not ready to yield the floor yet.
Oh, okay. No.
I hadn't noticed. So I wanted to comment on a second thing.
There's a leading question.
As I read this report, I'm not only struck by the science, but I think that the biggest thing that strikes you is the change since the early reports, like the Saul report in 2002. And what you're taken aback by is since that report, the U.S. has gone from leadership in high-power lasers to trailing Europe and Asia. And you ask yourself, why is that? And first thing you think about, well, did those guys do a lousy job with the Saul report? No, in fact, just the opposite. And in fact, not because the Saul report was wrong, but because it was right. And because Europe and Asia used it as a roadmap to invest in laser science. And this is where it's led. So then you ask yourself, well, why didn't the US take this more seriously if the others did? And I was reflecting on that, as I was coming here, and I remembered the era in which these reports came out. And remember in the mid-1990s, we closed down the superconducting supercollider in Waco, Texas. And there was a common rationale among policymakers that this made sense because the US didn't have to lead in everything, right? It could lead in some things and let other people lead in some things. And that's a compelling logic, but it has a danger. And the danger is it led to a kind of complacent atmosphere, if you will, where when this report was received, it wasn't received as a red flag warning. It was like, okay, well, maybe the US should lead in this, maybe not. But really, we should have viewed this as we should fight tooth and nail when we have a lead in something as important as this to maintain and build on that lead. And we're not so far behind now, but I hope we'll now take this report as a message that it is time to fight tooth and nail to regain that lead. Liz said push to lead, but I think it's push to regain the lead.
Thanks, Tom.